Whoops. Okay, so now I need to actually do it. So if I were to pick this point as my reference, so I'm going to take that away. What are the torques? So we have to have that the sum of all the forces is 0, and we have to have the sum of all the torques is 0. So the sum of the forces in the y direction so okay, what are all of those? So I have n1 up plus n2 up. Those are the only ones that go up, and those are going to have to support ml plus m beam or boom plus mc G. Okay, so how many unknowns do I have? Let's be careful here and keep track. So unknowns. What are they? N1 and N2. Okay, so I only have one equation, not good enough. I need to find another equation. So the sum of the forces, well, I'm not learning anything by summing the forces in the horizontal. I don't have any forces in the horizontal. So trivially, that's going to give me a 0. Okay, so it's not worth worrying about. What's the other equation that I'm going to need? I need to sum the torques about a point. And really, there's an art now to picking what point do you want to pick. It has to be true no matter where we do this. So does it matter? Usually, you want to pick a point that gets rid of as many forces as possible, because the line of action of the force passes through that point. Is there any place where I can get rid of more than one? I don't think so in this drawing. So any one of those points should be as good as any other. But I'll pick here just for grins. That got rid of N1, so that means that only N2 is going to show up, so that'll allow me to nail down what N2 must be, and then I can use this equation to solve for N1. Okay, so the sum of the torques must be 0 in equilibrium. And when I say the sum of the torques, that means I have to count clockwise as the negative of counterclockwise, right? So another way to say this is the sum of the clockwise torques must be equal to the sum of the counterclockwise torques. That's the only way we're going to be in equilibrium. Okay, so let's just blast through and do this. So, yeah. Okay, close enough. So what are the clockwise torques? Who's causing clockwise torques? Clockwise is that way. Okay, so this one, right? Okay, and so that would be m of the crane times g. What's the perpendicular distance? D over 2, I think. Anything else? Wow, that one is like all by its lonesome. Okay, so yeah. How about the counterclockwise torques? That's got to be everybody else. So N2 times D, except that in the limit, we're going to say what is true about N2. It's going to go to 0. Okay, I'll leave it in for the moment and then wipe it out. Okay, what's that? What about MB plus MBG? What's the perpendicular distance? So, yeah, I think it's L over 2 minus D over 2. Questions? That make sense? Okay, halfway over D over 2, halfway over on L over 2, but in the opposite direction. And one more is the mass of the load, so plus M load G, and that is applied at L minus D over 2. Okay, so balancing torques leads to MC G D over 2 must be equal to, now in the limit, that goes to 0. Okay, that's the limit when we're just about ready to ruin our day. And we have is equal to MB G L over 2 minus D over 2 plus MLG L minus D over 2. So, do I want to do that? Right. Yeah, we didn't even need that equation, right? So how are we going to figure out what's that? So if instead we picked the right wheel, yeah. Good. So from the upper equation, if N2 is 0, we get N1 must be equal to the sum of all the masses, L plus MB plus MC times G. Well, that makes sense, right? Because the only upward force is now being provided by the front wheel. And if that's true, then this will put a limit on the load that I can support. So I actually can use this to solve for the limit of that load. And that is, I want to isolate this term to tell me what's the maximum load that I'm allowed to pull up without tipping over. So MLG times L minus D over 2 is equal to MC G D over 2 minus MBG L over 2 minus D over 2. Okay, so the G's are kind of useless. And I can then solve for ML must be less than or equal to, in order not to have a bad day, MC D well, let's see. Yeah, mc d over 2 plus mb d over 2 minus mb L over 2 divided by L minus D over 2. Okay, so wait. Does that have the right dimensions?
Good luck. Yes.
Yeah, it's not that tough, right? In fact, I should tidy this up. How would I tidy it up? Multiply through by 2 seems like a good idea. So this would be MC plus MB D minus, ouch, MB L over 2L minus D. Okay, so provided that the mass of the bus is less than this, the crane won't tip over. So I guess we can conclude the mass of the bus was somewhat bigger than this, and that was the recipe for a bad day. Okay, any questions on this? So in order to be in static equilibrium, we need the sum of all the forces to be 0. We need the sum of all the torques to be 0, and it doesn't matter what point we pick to calculate the torques with respect to. But oftentimes, a good strategy is going to be pick a place that gets rid of as many forces as you can. In static equilibrium, we have no motion, no net torque, no net force, and I wish you a good day.